Hello, this is Chaitanya Belwal. In this video, I'm going to walk you over a derivation of a backpropagation equation using a very simple neural network. So you're going to use an article I have on my blog. I will have a link to the blog in the bottom description of this video. So this is just a walkthrough over my blog, and I will explain how each of the equations are derived. Now, normally in several books dealing with machine learning or neural networks specifically, they do give a derivation of neural networks, but they use a neural network which is a little more complex than it should be, especially when you're trying to understand fundamental concepts. One of my favorite books is the machine learning book from Tom Mitchell. This is the book on Amazon. So Tom's book has a very good derivation of backpropagation, but sometimes it's a little hard to follow through because he skips a few steps. So in this blog article, I actually have explained it in great detail, each and every step, even though it may seem very obvious. So it kind of makes it very easy to follow. So the neural network that we are going to use in this blog article is explained here. I have a single one input neuron, one hidden layer, and one output layer, and both the hidden and output layer have a single neuron. The RH value gives the result of the from the hidden neuron, and the RO value gives the output of the output neuron, which is will be a final output. So RH is mainly applied by the weight of the hidden neuron, which is represented by WH, and similarly W0 represents the weight of the output neuron. By the way, we're going to use a lot of calculus here, mainly partial differential equations. So if you need some understanding of that, I will highly recommend this video from Sal Khan at Khan Academy. These are some of the best videos on linear algebra, calculus, and a lot of basic mathematical concepts. So anyway, now in this neural network, you will see we don't even use an activation function, which is again just to keep things simple. In another article, which is part two of this, I actually add a sigmoid function for hidden and the output layer. But let's keep it simple for now. So this output, which is given represented by RO, that determines the error that we have. So let's say we have one training example that we pass through the input layer. It goes through the hidden and gives an output. The error that we compute as is given by this equation, where t is the actual value uh, of that specific output. So we will have a training data that in this case there'll be one value and this is what the expected value is. So if RO is different, the error is computed like this. Now this error is a very important equation because that error is back propagated to each layer. Now in this case we have only two layers, or actually one layer, the hidden layer where it's back propagated to. But in a deep learning network you can have multiple layers. So error is back propagated for till each hidden layer. And essentially what you're trying to derive is a change in weight of each hidden layer so that the error can be minimized. So what we're trying to find is E in relation to change of weights W0 and WH. So our input is fixed and our output we already know. So the values that we can control are the weights. So the hidden value weight is multiplied by the input, the output value weight is multiplied by the result of the hidden value. So let's first take a look how E changes in relation to the weight W0. So what we are trying to find is the rate of change of E with respect to uh, the weight of the output layer. In this case, I will just use layer and neuron interchangeably because we only have a single unit. So E is given by this, then you do a partial differentiation here. Now in this case, since we have only one neuron, we can actually use a full differentiation. It really makes no difference. But just I'm using the same term that have been used in other machine learning books just to keep it simple. So rate of change of E in relation to W0 is the rate of change of this equation of E with W0, which actually gives us equation 1.1. So if you're familiar with calculus, this equation, this 2 over here becomes is a constant and it comes out. So we can take this 2 in the denominator and extract it out of the differential equation since it's a constant. Now let's revisit the chain rule. Now chain rule is very fundamental to understanding how propagation works. The chain rule is a very simple equation which says if you have a dx by dy, you can break it up into rate of change of x in relation to z and the rate of change of z in relation to y. Same thing can be expanded for a partial derivative where partial uh, rate of change of x in relation to y can be a partial derivative of x in rate of change of x in relation to z and rate of change of z in relation to y. Now let us apply the chain rule to this equation 1.1 here. So let's make z equal to t minus r0, x equal to z square. So this t minus r0 square becomes x and y is equal to w0. The reason why we are applying the chain rule because otherwise it's going to be not pretty difficult or there won't be any straightforward way to do a derivative of this term here. Anyway, let's proceed. So this was the original term for equation 1.1. So we just copy it here and just say this is equal to half x by y because x is equal to t minus r0 square, which is the value of z, and wo is represented by y. So applying the chain rule, we break it up into x by z and z by y, as has been given in this equation for partial derivative. Now we replace the value of x with a z square, and then we leave z and y as is. Then we put the value of z, which is t minus r0, which becomes t minus r0 square, times t minus r0 upon w0. Now you'll recall we could have actually done a simplification here. So the z square, if you recall calculus, any x squared to the power of x or rate of change of x squared to the in relation to x actually equals 2x. So this becomes 2z or 2t minus r0 and this term remains as is. So we will have to further do some kind of further analysis of this term t minus r0 over w0 because both the terms here and in the denominator are different. So we are trying to find the rate of change of t minus r0 in relation to w0. Now recall r0 is equal to w0 times rh as given in the original neural network. So r0 is equal to w0 times rh. So we put the value here. Now this is a subtraction term, so we can break it up into individual derivatives like this. So t, we're trying to find the rate of change of t in relation to w0 and the rate of change of w0 times rh times w0. So rh is a constant here, so we pull it out. So we keep this as t w0 times rh w0 by w0. Now t again is a constant, so the rate of change of a constant in relation to any other term is basically 0. And then a rate of change of x times x is also basically 1. So we extract this term becomes rh times 1. And here we have given an explanation why we have done this change. So using this term over here, this is equation 1.2 where we say this term here is equal to the term here. We copy it as is. Now we know the value of t minus r0, which we have computed over here. It's simply minus rh. So putting the value of t minus r0 plus the replacing the actual value of this partial differential equation, we get 0 minus rh and a final result is t minus ro times minus rh. Therefore, if you look in the original equation where we try to find a partial derivative of E in relation to W0, which is the equation that we have given in the very beginning, this one, we turn it into this term over here, and this whole term is the value of the rate of change of E in relation to W0. Now recall that RH is equal to WH dot I, which is given over here. So we replace the value of RH with the actual raw value, which is based on the input. So the T minus R0 becomes WH times I. Now all these values are known, so there's no further derivation that we need to do. Now let's apply this similar concepts for how the error changes with respect to the weight of the hidden layer, which is WH. So again, dE by WH, we already know the value of E, T minus R0 square upon 2. And then on the denominator, we are trying to find the rate of change with respect to the hidden layer weight, so it will be WH. So let's call this equation 2.1. Again, applying the chain rule, we put Z is equal to T minus R0, X is equal to Z square, and except the only value changes that Y is equal to WH now. In the previous derivation, it was WO. So applying these values here, we get following through, we get the Z square by Z, dZ by dy. We put all the values. The only term that is different is T minus R0 upon the partial derivative for WH. Now let's proceeding further. Let's derive for this. So T minus R0 upon the derivative of WH, we put the value of R0 in, which is W0 times RH. As RH again is further equal to WH dot I, we replace this value here. So this terms become a partial derivative of T minus WO times WH times I upon partial derivative of WH. Going further down, deriving this, now WH upon the derivative of WH, if we treat W0 and I as a constants, these come out of the partial derivative as shown here, and we do a derivative of WH by WH, which basically is 1. So again, as before, the partial derivative of T with respect to WH is 0 because T is a constant, and the value becomes minus WO dot I, where WO is the weight of the output layer. So let's put this value in equation 2.2. Now we have derived this term over here. Let's apply this. So T minus R0 WH is equal to minus WO dot I. So this is the value we get for this term. Now this term essentially is same as the rate of change of E with WH, which is the hidden layer weight. This is the term that we get. Now, once we have determined the rate of change of E with respect to the output layer weight and the rate of change of E with respect to the hidden layer weight, we can deduce how we update our weights. So normally what we do is we calculate a delta W0. This is for the output weight. We multiply it by a learning rate times the rate of change of E by WO. So this value eta is the learning rate. We multiplies by the value, and then the final value of W0 is computed at the original value plus the delta. Now, one of the important things to remember here is that the delta W0 mainly determines the direction. We actually do not need to use the full values that are determined like WH.I. In fact, there's another method called alprop where we just take the sign of this value and just increment or decrement it simply by the learning rate or eta. But in this case, since we are following a standard backpropagation, we'll do as per it's explained in the textbook and in the original paper. So similarly, we do it for WH. Again, the sign is very important. That is determined for delta WH. That tells us whether we increase WH or decrease WH. The decrease or increase amount is again eta times the value computed by this. Again, as I mentioned before, in the rprop, we don't use this term over here. We just simply use eta and extract the sign out of it. Then we apply this either using stochastic gradient descent, where we update the weights for each training example, or do more for standard or batch gradient descent, where we update the weights after exhausting to some examples or the entire training set. In part 2, we will take a look how to derive the backpropagation when there is an activation function. So you can visit my blog and read the article, and I will also upload a video in the coming days. Thank you for watching.